Mesdames et messieurs,
Good evening, ladies and gentlemen. Welcome to all those who are here on Monday and Tuesday evenings and who come back to join us this evening for this third lecture on the 19th Right Colloquium. The subject today, well, you know, is a conference which should have been live. In fact, the auditorium has a space for 600, and there are hundreds more following us on their screens. And I'm sure that there are going to be more this evening. My name is Olivier Thibault. I'm a journalist and a director of scientific communication for the Geneva Science and Diplomacy Foundation. I'm very happy to be in charge of the presentations this evening. As you know, every year we have a privilege to welcome at the University in Geneva speakers of great renown. This year is not an exception. We've got a whole range of mathematicians, incidentally, who, with their presentations, with their lectures, may remind you of what it was like being back at school. And these persons are involved in fascinating academic research, dealing with very specific things, because mathematics is not just a toolbox for sciences or the other sciences. Research areas are vast fields. It's something that's very lively, which go well beyond the academic field. And you'll see their applications in industry and finance. And it also helps us to explain the world. Galileo at the time, who said, and I'll quote him, "You can only understand the universe if you understand the language and the characters in which that language is written. Nature is described in a mathematical manner." And you will see that the lecture this evening is very much in line with this adage. Now, this evening is going to take place in two parts. First of all, the lecture, then there will be a question and answer session. It will be done online, and I will explain this to you in a few moments. Let me give the floor to the president of the Wright Foundation. It is under their patronage that this conference is taking place, and it is a foundation which really promotes dialogue between science and society.
merci.
Thank you. Ladies and gentlemen, good evening. The Wright Foundation is very happy to welcome you once again this evening, and I'm sure that you're comfortably seated in front of your screens at home, and we hope that you're going to really follow something which is of great cultural importance. Since the beginning of this week, we've seen how mathematics and other spheres of life are able to cross-fertilize, how we are able to understand nature, and physics in particular, by having mathematical tools which are necessary to decode them, and how nature allows us to develop our intelligence. For example, how sometimes the result of mind games without any physical representation are at the center of the description of large swathes of nature. I think it is also fascinating to see how very simple models, far from physical complexities, may suddenly show how subtle they may be and rich in teachings. So we're going to continue in that vein this evening, listening to Martin Herrère, who is going to be talking about the smallest elements which are accessible by physics, and at the other end of the scale, what is limited by space. And I'm sure that we're all going to have a very lively and interesting evening, and I look forward to hearing him. Thank you very much, Thierry Courvoisier. Now, we were saying that this is going to be as interactive a session as possible in spite of the conditions. So you have the possibility to ask questions to the speaker of this evening. You can do so online. So those of you who are following us on the Colloquium's site, there is a little white box. Please insert your question in that box. And those who are following us on Facebook Live, please also go to the Colloquium site and ask your question. You can do this in French or in English. We are fortunate enough to have an interpretation at this conference in English and in French. In fact, if you want to follow the conference in English, there is a button that you can press so that you can switch to the English language. And the interpreters are with us here, allowing us to translate this series of conferences into English. So, our speaker this evening Now, you've probably seen his name in the media. He got a new science prize, the Breakthrough Prize. He won a few weeks ago, which have been added to others. He won the Fields Medal. He won that prize in 2014, which is the Nobel Prize for mathematics, if you want to make an analogy. Mathematicians consider that this is their Nobel Prize. Martin Heyer is the most Genevese of all the speakers this year because he did most of his studies here. And I'm going to ask somebody who also taught here in Geneva and who knows him very well. And I'm just going to ask Jean-Pierre Ekman, who is honorary president of mathematics here in Geneva, to come and introduce Sir Martin Heyer. Thank you and good evening. Now, you've already heard the prizes that Mr. Heyer has won, and I'm sure you've also heard that certain Martin Heyer has not only won the Fields Medal, but he also won some very important other medals. But perhaps what is less known about him is that since his birth he's been a citizen of Geneva, although he actually carries an Austrian passport. So, I'm going to go rapidly through the period of time he spent in Geneva. His father lent me a few photographs which I want to share with you. He was born on the 14th of November 1975 at the Bois Gentil clinic for the Genevese amongst you in the audience, and his parents lived in Verrières on the outskirts of the city. You can see his mother with him, and you can see him against the Salève mountain with his brother and his sister. He was the eldest of the three. Now, I wanted to show you that he had a lot of hair at the beginning when he was a child. Now he doesn't have so much hair. He did all his schooling in Geneva. He went to the pre-secondary school and he went to Claparède Secondary School. As his father was professor of mathematics at the University of Geneva, he became interested himself very early in mathematics. This is in Seoul, where he received the Nobel Prize. You can see his father on the right-hand side, Ernst Heyer, and Soumé Lee, his wife. I will show you how he became interested in mathematics. I hope it's legible. At the primary school, he says, I want to be a mathematician when I go to university. I want to be a mathematician because I am really interested in this subject. My father, who is a professor of mathematics, taught me 3 years ago how you could draw a curve based on a simple formula. A bit later, at my request, he explained to me how the sinus functions. And then 6 months ago, or 6 months later, I should say, he taught me how he started to get interested in statistical calculation. And I observed the signification of several signs which refer to statistics which were completely obscure to me until then. And as Hugo was saying, some things are or seem obscure in mathematics. However, I wanted to continue my studies in secondary school, and later I wanted to continue mathematics at university level. But there is another aspect of Martin Heyer's background, which is perhaps a little less known. He participated in the Schweizer Jugendforsch, which is Swiss Youth Researchers. He participated in this on 3 occasions, and he produced a program which is called Amadeus, which analyzes sounds. For copyright reasons, I didn't enlarge the picture too much, or the advert for the program, but you can find it on the web. In any case, it's a major commercial success. Martin then carried on to do his studies at the University of Geneva, as you've heard. He studied theoretical physics, but apparently this type of education was sufficiently advanced to transform into a more than respectable mathematician. And as is well known, he won the Fields Medal in 2014, and he celebrated this win with his parents. And it is his mother who produced a large cake with a Fields Medal in marzipan to decorate the cake. But he also celebrated with all those who studied with him. You can see the team behind him or next to him. Let me just also point out in finishing this introduction that around the table there was John Jones, who also started his studies and who is shown in the cafeteria and who's no longer with us. So I hope that you will enjoy the trip of the infinitely small to the infinitely large with Professor Hira.
Merci beaucoup.
Well, thank you very much. Thank you, Jean-Pierre, for having introduced me. And let me start by saying that I am very happy to be back in Geneva, at least virtually. And I would also like to thank the organizers of this colloquium, in particular Thierry Courvoisier, Mr. Alexeyev from the Scientific Board. For tonight's conference, I'd like to start with showing you a short video which was made by an Australian astrophysicist whose name is Daniil Obreshkov. In this video, you start with a subatomic scale. What you see here is supposed to show protons and neutrons within the nucleus of an atom, and what you see in colors is supposed to represent quarks. And then you can zoom out, and every 3 seconds you multiply the scale by a factor of 10. So after a few seconds you see the whole of the atom. This cloud is the cloud of electrons, and then a few seconds later you reach the scale of molecules. This is a DNA molecule. You see this DNA molecule is within a cell. Then you see the nucleus of the cell. You see this is a white cell, which you can see within a blood vessel in the eye of a person. So you reach the scale of a centimeter, then the scale of a meter. This is the usual scale which everybody knows, but you go on zooming out, and very rapidly you reach the scale of a whole country. This is the scale of 1 kilometer, then 10 kilometers, 100 kilometers, and soon you see the whole Earth appear. Several thousands of kilometers, then many thousands of kilometers, the orbit of the moon, the size of planets of the solar system, the other planets, then the belt of asteroids. A few seconds later, you see the whole solar system with all the external asteroids, the closest stars, the mass of stars where we are, then the Milky Way with thousands of light years away from us, and all that within a few seconds. Then these masses of galaxies, and at the scale of 1 billion light years, this is the whole of the universe with huge masses of galaxies. What you could keep in mind, after seeing this video is that the way we used to write down numbers is taught at school with powers of 10, and this enables us to show huge numbers. As you've seen in this video, we started from the smallest possible scale, the scale of subatomic particles, and then we ended up with a huge scale of the whole universe within 2 minutes. That means about 40 scales of magnitude, from 10 to the minus 15 to 10 to the 40th or 41. If you did the same with time, and if you wanted to measure the age of the universe from the smallest possible scales, in other words, atomic vibrations, you'd reach about 10 to the 14th or 33, and you could cut up the story of the universe, the whole of the universe, and you cut it, if you cut it out in particles, you would be able to see all the instants of time. That would lead you up to 10 to the 150th for all the instants of the universe from its beginning to now. This means, in other words, that 10 to the power 150 is already more or less infinite for all practical purposes. Because if you take the smallest possible thing in the universe and you use it to measure the biggest possible thing, you reach a level of about 10 to the 150. To give you an idea of the scale of magnitude, you probably all heard about the paradox of the clever monkey, which says that if you have a monkey typing on a typewriter more or less at random, and you wait sufficiently long, that monkey will be able to type in the whole of Shakespeare's work. Of course, this can never happen because it would last longer or take longer than the whole age of the universe. Well, that is not quite true because the difference in scale is absolutely huge. If you just concentrate on one page by Shakespeare, for the monkey to be able to type in correctly one page of Shakespeare, you'd have to wait 10 to the 4,000. So the huge number, the biggest number possible that we know about the age of the universe is 10 to the 150th, but 10 to the 4,000 is even incredibly more. So it has no sense, no meaning at all to say that you'd have to wait as long as the age of the universe to see this monkey type in Shakespeare's works. That doesn't even begin to describe it. This gives you an idea of the huge size of numbers that you can reach if you work with powers of 10. The numbers you can reach are absolutely unimaginable and for all practical purposes actually infinite. The other thing that you can see thanks to this video is that the behavior of nature is different if you change the scale you're looking at it. If you see the scale of atoms, of the human beings, of the universe, well, you notice that the universe has a different behavior from the behavior of other scales. And yet, the laws of nature are the same. Let's take the laws of the fluid. Water, for example. I'm sure that you've all seen, if you walk past a pond, these insects which actually walk on the water. This is the picture of one of such insects. If we tried to do the same thing, obviously we wouldn't succeed, with a few exceptions maybe. But in general, at the scale of the human being, water has a very different behavior from its behavior at the scale of such insects. In particular, liquids have a specific property. The smaller the scale, the more viscous they seem. This picture shows you exactly the way water behaves under the feet of this insect. This looks more like honey than water, whereas at the scale of human beings, water looks more like this. It's much more turbulent. And the reason for that is astonishing, because the equations which describe the behavior of water at these two scales are exactly the same ones. These are, however, nonlinear equations, and the terms of these equations are important, but at different scales. To illustrate this, I could take the example of an image. You could imagine that this image represents the laws of nature. This teapot, containing quite a few details, could be zoomed in. And the more you zoom in, the less details you see. And very rapidly, everything becomes monotonous and you see only one color, which is not really interesting. Or maybe you can try and see something more interesting. You could zoom here at the interface, but even then it's not very interesting. There are simply two colors separated by a line. However, the image itself is always the same. It's just that it's being looked at different scales. If you see it from too close, all the details have disappeared, and they simply cannot be seen any longer. So at that scale, these details do not matter any longer. However, other images which can be easily described in mathematical terms are more interesting. This image of the teapot, of course, has been drawn by an artist, but the way it has been represented by the computer is simply a mathematical formula. Rather complicated, yes, but not that much. However, the image you see here, Mandelbrot's set, is also the expression of a mathematical equation, a simpler one actually. But that image remains interesting even though even if you zoom in. Let me concentrate on that part, for example. You see here that kind of spiral, and if you zoom in into that spiral, you can see it closer, but somewhere in the arm of this spiral, you see something different, and then you can zoom in again, and you see this, and then you zoom in again, and you see that. Once again, you see a spiral that looks a bit like the previous one, and then you zoom in here, and you see something differently. What you see with this example is an image which can also be described, or is described, by a relatively simple mathematical formula, but presenting details that are visible at every scale. If the initial image was big like a piece of paper, you could zoom in up to the atomic or subatomic scale, and you would still see very interesting details. And that is what you call a fractal. A fractal is precisely an image showing details whichever the scale is you're in. But it's also interesting to study models describing elements of reality having that kind of fractal behavior. In other words, interesting behaviors, whatever the scale. Let me take an example. Etienne Gis mentioned it already on Monday. This example is Lorenz's system. For those who attended the first conference, you know what it's all about. Around 1960, Lorenz proposed a very simplified model of atmospheric conversion with only three quantities or three values changing with time, which we call x, y, and z, just like the coordinates of a point in space, which changes with time. And these rather simple equations, which can be written in 3 lines, describe the evolution. What it means here is that this velocity of the point at a certain point with the coordinates of x, y, z is given with these equations. And if you solve them, you obtain that kind of figure, that kind of curve. Horizontally, you have the x coordinate. Vertically, you've got the z coordinate. And if you start from any point and you solve the equation, the trajectory will be something like that. What you see in this image is 2 or 3 of these trajectories. Etienne explained already in his presentation on Monday that this Lorentz system is a prototype of a chaotic system. In other words, essentially it is impossible to predict the behavior of these trajectories beyond 2 or 3 laps. In particular with this example, if you see the evolution of this system, essentially you have these 2 points around which the system tends to revolve. And sometimes it goes from one of these points to the next one, starting with this one, then going to the other one and back and forth. What could be predicted would be in which one of these 2 lobes you'll find yourself after a certain time. And you could wonder what kind of precision you need at time 0 to be able to predict with certainty in which one of these 2 lobes you'll find yourself. This precision is about 10 to the minus 0.4. The time you need to go around a lobe is about 1 second, which means that every 2 seconds or every 2 units of time, the precision you need to predict where you'll find yourself, in which lobe you'll find yourself, is multiplied by a factor of 10. In practical terms, you are never in a position to predict more than 20 revolutions in advance, because 0.4 times t is 10 to the minus 10. That would be already the atomic scale. Obviously, as a mathematician or a physicist, there is an interesting question to be asked. Since it's impossible to predict with any kind of certainty in which one of these 2 lobes you'll find yourself, even if the solution to the equation is totally deterministic, what can you possibly say about this evolution? Etienne explained on Monday that it's possible to predict statistical quantities. Obviously, you can indeed. You could, for example, calculate statistics with the centers of these 2 lobes, and if you calculate a statistics of the place where the x coordinate will be found out, you'll probably get a kind of curve like this, which means that the curve will go around this point or the other point. And this statistic is stable, which means that the curve, it looks more or less always the same. But today I'd like to mention something else that can also be predicted on the basis of such a behavior beyond the statistics of that was mentioned earlier. It's possible to interpret one of these coordinates, for example the first one, as being a velocity and draw the position as a function of time. If this is interpreted as a velocity, it means that the velocity is positive if you are here on this side and 0 is in the middle. The image is totally symmetric. When you're here, for example, the velocity is positive. If you're on the other side, the speed is negative. So what I'm drawing here on this curve is along a trajectory. If I am at the right of the curve, I go up, and if I'm at the left of this curve, I go down. The first coordinate is therefore interpreted as a spatial coordinate, and I plot the velocity. Every time the trajectory is on the right, I'm going up, and every time I'm at the left-hand side, I'm going down. If I'm close to the center, then I probably stay at a planar level or horizontal level. This is then what I see. This is a plot after 5 revolutions, but on the longer term, I'd probably have a curve like this, going up and down, and then up and down again, and up again. With a longer time, it seems to have a very erratic or random behavior. With a time of 5,000, I see this very irregular trajectory. I'd like to be able to say something about this trajectory. But you see, it's impossible to predict with certainty, even if I know the initial condition here, it's impossible to predict whether it's going to go up or down at that other point in time. What you observe there seems similar to a very simple random model, just like playing heads or tails. If you take a coin and you throw it in the air, when it falls, if it's heads, I win. If it's tails, I lose. So you start with a certain amount of money and you lose 1 franc or gain 1 franc, as the case may be. And you can plot how much money you've gained or lost. So start, I'm having heads, and then I gain 1 franc, gain again, then I lose, then I gain, etc., etc. So in the end, what I get is a trajectory which seems a bit like a caricature of the trajectory which I mentioned or observed earlier on. There again, the question can be asked, what's the behavior going to look like after a great number of games? If you play that game for 3,000 times, you come up with a plot that looks very much like the one that was extracted from Lorenz's system. But maybe it's just a matter of chance. Maybe it's a matter of a coincidence. Maybe any random event is going to look like that. Well, I'm going to try and convince you that this is not a coincidence at all. These two models, at that kind of scale, are not simply looking like each other. They are the same in mathematical terms. This specific model is called Wiener's process, or Brownian movement, if you're a physicist. And historically, it has been studied by Brown to start with. Brown was a biologist who lived, I think, in the first half of the 19th century. And what he did was he looked under his microscope the behavior of pollen particles suspended in water. And he noticed that these pollen particles had a very erratic movement, even though water was completely still. So, having no external influence explaining this movement. And the open question that remained open for a very long time was, is it possible to study the movement of these particles and get a good mathematical model? Einstein and Smoluchowski developed independently from each other at the beginning of the 19th century. This is on the left-hand side Einstein, and the other one is Smoluchowski, who was a teacher, professor at the University of Vienna at the time. They both developed at the beginning of the 20th century, a theory of Brownian movement, which has two parts. In physics, this theory says that the reason why you see a Brownian movement is that these pollen particles collide with water molecules. These big pollen particles, well, big for the scale of water molecules, you've got these water molecules which are quite smaller next to the pollen, but everywhere, and these molecules of water move around just a bit like billiard balls, and when they collide with the pollen particle, they kind of push it in one direction. If this water molecule collides with the pollen, then the pollen will move in that direction. And then you'll have probably a collision from the other molecule, and then the pollen will move in another direction. So the theory says that the total of these collisions creates a macroscopic movement that can be observed. Another part of the theory was linked with mathematics. This movement could be described, but since it is a random movement, you can't predict it with any certainty. The only thing you can predict is a probability. And in this specific instance, what Einstein and Smoluchowski maintained was that the probability, since the pollen particle was at a certain point in time, at a certain place, the distribution of probability of where this pollen particle will be, let's say, for example, a second later. And the distribution of this probability can be described with an equation called the heat equation, which describes the behavior of heat precisely, the diffusion of heat in a solid body. This Brownian movement theory enabled both researchers and others to make quantitative predictions. Particularly Perrin was able to receive the Nobel Prize in 1908 for that. And the reason why he received the Nobel Prize for that was that he made an experimental verification of the equation, which made all the other debates completely moot. At the time, people were reluctant to accept this, but he was able to prove very scientifically speaking, that there was no other explanation, that this was the right explanation indeed, and you could verify it experimentally.
Ce même mouvement brownien
The same Brownian movement at the same time appeared in the thesis of a young man called Bachelier, who submitted his theory on speculation at the beginning of the 20th century. Now, unfortunately for him, he wasn't extremely successful. The probabilists of the period were interested by mathematics, pure mathematics that is, and they didn't want mathematics to be used to describe things which were very materialistic, for example, the rate of the stock exchange. So they didn't really support Bachelier. And Bachelier never really got a university position. The first position he got at university, I think it must have been in Bordeaux, and that was at the age of 57. He gave private classes before that and taught in secondary school. Now, he was interested in the stock exchange and developments in rates on the stock exchange. And he described a mechanism which could explain the evolution of rates on the stock exchange. Now, if you take, for example, the price of a share, for example, a Google share, what is going to get the price of that share to change is you're going to have people buying and selling that share. And every time somebody buys the share, the price will go up, and everybody sells, then that price will go down somewhat. When you and I buy or sell shares, there may be small amounts involved. And so the effect is going to have virtually no effect on the price of the share. It's like the collision of one molecule. The pollen will not affect the collision, but if you've got billions of molecules which are in collision with the pollen, that's going to give you a macroscopic collision. And that is the same thing for the stock exchange. If you've got hundreds of thousands of people who buy and sell shares, each of these transactions has a negligible effect per se on the rates and on the amounts of value of the stock exchange shares, but the cumulative effect is actually something that you can see. And in his thesis, you've got a mathematical explanation. It's the same description as in that of Smolosowski and Einstein, and that established the basis for modern finance, and in particular for the work done by Black and Scholes, who in the 1970s developed their Black and Scholes formula, and that was used for a put price, and they got the Nobel Prize for Economics in 1997 for that work. So what you can see here is the same mathematical theory, which is shown here by the distribution of probability given to you by the heat equation. That is to be found in completely different contexts. It's equally true for the rates on the stock exchange. It's also something that can be used to describe the Brownian effect. And intuitively, it's basically the same thing. You have a mechanism which allows the price of the stock exchange to go up or down, or to move the pollen to the left or the right. And the mechanism in question is that you're going to have a lot of small events which appear to be independent and chaotic. Each of these small events has an infinitesimally small effect, but the cumulative effect is large. And that is exactly the same thing with this game of heads or tails. If you've got three 1,000 games. Each individual part or each individual game will contribute very little to a final result or to the final prize that you may win. But if you look at the accumulative effect of 3,000 games of head or face, even though everything seems to be completely independent and random. In the example of the Lorentz system, intuitively, you can see the mechanism is basically the same. In other words, you've got this chaotic evolution with the two lobes, and it seems to be chaotic, where you have movement from the left to the right lobe and vice versa. And you can see that curves will go up or down, down if you're on the left-hand side, up if you're on the right-hand side. So we have a mathematical object, which is an ideal object or idealized object, which is the Brownian movement, which provides you with a continuous random curve and which describes the behavior of all the systems I've described on a very large scale. So you can see that all these systems on a large scale are described by exactly the same mathematical object. This mathematical object has a particular attraction. You can zoom for as much as you want. It continues to behave in a very interesting manner. You don't see just a straight line. And it is autosimilar. So you can zoom and you'll see the same distribution. Statistically speaking, it's exactly the same curve, even though it evolves, but the statistics remain the same. This intuition we have here, which is that systems which behave similarly, but not in an identical manner, but if you look at them on a larger scale, they start to behave in a very similar fashion. And that intuition was developed by Wilson. Wilson was a physician. I think he got his Nobel Prize in 1980. And in the 1960s, he developed a theory on standardization curve. And his theory was, when you speak of a mathematical theory which describes a physical object, and if you ask whether two theories are close or whether they describe similar products. Now, there is no reason just to compare the two theories in order to look at the mathematical parameters of the two models. What you need to do is to fix a scale of magnitude, and you've got to be able to compare the physical predictions which are relevant at this particular scale. So, to compare mathematical models which describe the physical world, you're not just going to compare models, but you're going to compare models at a particular scale. And if you do that, you have a natural dynamics in the space of models, which is the dynamics of the change of scale, which is exactly what you saw in the video at the beginning. At the beginning, what you saw is a physical system, which was the universe in its entirety, and then you changed scale. You started to see something at the microscopic level, and then you zoomed up to the level of the universe. Wilson explains to us that it may be useful to imagine that you have a space of physical theories, which is shown in this drawing. In other words, this is a space of physical theories. You have natural dynamism, which is shown by these arrows here. And that dynamism, that is a dynamism of zooming. You're changing your scale, and even if you are looking at the same physical theory, you're looking at it with a different scale, and there it behaves differently. So this begs the question, in this space of theories, are there theories that are more interesting or more relevant than others? And more specifically, are there theories which are fixed points? In other words, it's a theory which does not change when you change scale. That is something when we looked at the Brownian movements. You had fixed points, a fixed point. You can change scale as much as you wish. You saw that video I showed you earlier on in the Brownian movement. I can change scale as much as I want, but it remains the same theory. It behaves in exactly the same manner, and so it corresponds to a fixed point in this space of mathematical theories. Now, if it is an attractive fixed point, it means to say that there are lots of other theories, and when you zoom on a larger scale, they behave like this theory on Brownian movement. And that is exactly what we saw in the different examples I showed you. If you wanted to have a mathematical description of a heads or tails game, it's quite different than when you have a mathematical description of the Lorentz theory. And it corresponds basically to two different points in this space of theory. But when you zoom up to a very large scale, when you look at the other points of the theory, the two theories have exactly the same behavior. They converge towards the same point. So that moves in the direction of a possible explanation, and of course there are many other explanations, but moves in the direction of the famous Widner's experiment, which spoke about the unreasonable efficiency of mathematics. And the idea behind this was, how come mathematics is so efficient in describing nature? Now, that's a very profound point, which has been the subject of debate for a very long time. But this is a small element which gives a new perspective on this aspect. I've spoken about Brownian movements, and this dates back to the beginning of the 20th century. The mathematical description came a bit later, but this was done in the first half of the 20th century. Now, let me show you something which is relatively similar, but which is much more recent. This is the fluctuation of interfaces. Imagine you have a situation, a two-dimensional situation, when you've got two regions. You can see a forest fire here. You've got this part which is burnt, and you've got this part which isn't burnt yet, and you've got this flame area which separates the two areas. And this flame base is moving towards the right, and you can see that there are random fluctuations. It's more or less straight. You can see the basis of the fire movement, but at the same time you've got random movements shown here, which are random movements around the straight line. And what we would like to be able to do is to describe those fluctuations. Now, we've got other systems which behave in the same manner. What I'm showing you is a microscopic photograph of a liquid crystal. You can have a stable and an unstable phase, two phases, and the stable phase is separated from the other phase by this interface. Or we could take other mathematical models which represent this kind of situation. A game model would be a model, for example, with bricks, which are placed one on top of one another. And the way that this functions is that the bricks fall from the sky, and they keep falling, either until they fall on bricks that were already in place, or they will perhaps, if you had 3 or 4 bricks which had already fallen, but if you have a brick that falls to the one side, it is going to be stuck to the brick next to it. It won't fall to the bottom. So if I take this system, you have the impression that this has nothing to do with liquid crystals or forest fires. But it gives you a model where you have a region with bricks, and you have an interface above it, which is the area above this set of bricks. I'm going to give you a simulation of this stack of bricks. And the stack of bricks gets bigger and bigger. And you can see this at a very large scale. And you have the bricks at the bottom, and you have a more or less straight interface, but you also have a random movement in that interface. In such situations, you will see there are 2 classes of universality. You've got 2 of these fixed points. One which is named after Edwards Wilkinson, which is a symmetrical class where you've got the 2 phases are stable, and you're going to get a symmetrical movement in the 2 phases. And then you also have an asymmetrical system, such as the one I've just shown you, where you have the 2 regions which are in phase. These are theorems for certain models, but for some of these theorems, they're just conjectures. But you look at the number of interfaces that you can describe in mathematical terms. When you look at them on a large scale, and they will converge. They will converge either towards this Edward Wilkinson or towards the Ekpz asymmetrical class. There is a very recent theorem which says that the Ekpz fixed point, which was imagined in the 1980s in the literature on physics, that Ekpz fixed point actually exists. The analogy would be the Brownian movement, which dates back to the beginning of the 20th century. In this interface fluctuation situation, what we are dealing with, and this is something that came up 3 years ago, where you can have an idealized mathematical object. And this will apply to lots of different interface models. The other question that we need to ask is that for this dynamics, there are certain models which are inserted by the symmetrical, other by the Ekpz asymmetrical system. What about those systems where you're between the two, where you've got Edward Wilkinson being the prime attraction, but which are going to be more attracted by Kfz on a very large scale? So the question, is there an idealized model which would be Ekpz on a large scale and Edward Wilkinson at a low scale or at a smaller scale? And the question is this unique? Is there just one, or are there several? This is a mathematical model I've worked on for some time over the last few years. And we are able to show that there is an object which is called the Ekpz equation, which was described by K, P, and Z. This was an equation which was formulated in the 1980s. It is a stochastic partially derived equation which shows about mutations over a time-space continuum. And the solutions are very irregular. At every instant, the solutions look at a Brownian movement in space. In other words, they are self-similar, but they're very irregular, as is to be expected in the Brownian movement. I'll give you something like this. And they are so irregular that the slope is infinite at each place. You have this infinite point at each space. In this equation, this is the square of the slope. So if the slope is vertical, it is infinite. And then the square of the slope is infinite. So you have an equation which actually doesn't make sense, because on the right-hand side, the slope is infinite. So you've got to have an infinite constant which can be subtracted. So the theorem, it's not a single theorem. Actually, it's a group of theorems developed by a number of different persons working in cooperation with many persons. So there is a notion of solution, and the solution is stable under disruption. As you have this, infinity has to be interpreted in the proper manner. You have the impression that there are several ways of interpreting this, and that you could end up with different possible solutions. Now, if this were the case, it would suggest that there are several models which link these two fixed points, but it's not actually the case. So you've got a notion of solution which is very stable. So this is very much part of contemporary mathematics. And it is the beginning of another story in the field of standardization, which is based on how you interpret models where constants want to become or tend to become infinite. But that is a completely different matter, and I won't talk about it today. And perhaps I should stop now and say thank you for your attention, and I'll take questions. Thank you. Thank you very much for that very interesting presentation. You now have an opportunity to ask all the detailed questions on these equations. You can ask questions in English or in French. Use the interface on colloque.ch, colloque.ch. I am very happy to have Eric on stage with me, who is going to participate in this discussion. I'm going to start differently this time with you, Martin, and I'm speak about you. Now, we have seen your background, and you said when you were a young boy that you wanted to do mathematics, but you did physics at university, and in fact, you also studied computer science. No. Okay, so let's just say that you studied mathematics and physics, but you seem to be drawn by both. So I wonder, is it physics or the observations of the physical world which nourish your mathematical reflections, or is it the mathematical object which you apply to physics, and is it that you focus on? Which is the domain which nourishes the other the most? That's a very personal question in a way, because I think that different people would answer that question differently, and each answer would be valid. For me, I go from physics towards mathematics. What we want to understand is mathematical models. It's the mathematics that interests me. But physics is a source of inspiration and a source of intuition, I would add as well, a source of intuition for mathematics. So personally, I like the kind of mathematics which I can represent in relatively concrete terms. So that's mathematics which are linked either directly or indirectly with physics. Is everything a source of inspiration in physics? You're talking about coffee which is going to be spilt on the sofa as we were preparing this presentation. You could tell how the stain was going to spread in the material. Can you apply that to other areas? I suppose so, but for me, it's mathematics that come first. So what interests me in the example that you've given me where a cup of coffee is spilt, it could be a cup of tea, but it would be the behavior of the local effects of these equations. These are questions which are connected with reality because we have descriptions of the behavior of a fluid, whether it's water or air. But the final analysis, the questions that I ask, are based on a mathematical motivation.
When you got the breakthrough prize, you said, one thing I like about math is that it has this kind of permanence. And then in 2014, in another paper I wrote when you had the Fields Medal, Nicolas Monod said that you tried to find aestheticism and pure truth. After the conference, I talked to Mr. Ekman, and he told me that maths have something more than physics, because maths are more true than physics. Maths are true forever, which is not necessarily the case in physics. Do you have that kind of absolute truth in maths? Do you find out? Well, I think all mathematicians are looking for this perfect truth. And it's true that is what attracted me to mathematics. As you said, precisely, in mathematics, once you've demonstrated a theorem, well, theorems are demonstrated by human beings, and it's possible that there is a mistake in the demonstration, but in theory, it's possible to formalize a demonstration in a way that can be verified by someone else to make sure that there is no mistake. It's not very convenient, but in theory, it's feasible. Once a proof has been understood by a sufficient number of mathematicians, you can be pretty sure that you're quite close to an absolute certainty of the validity of the proof. So once you have a valid mathematical proof, it's not going to be questioned any longer. Maybe the theorem in question is then later on replaced by something more general, more elegant, more eloquent. That may happen indeed. But you'll never have the case where from 1 second to the next the theorem will be completely forgotten. Mr. Ekman, do you want to add something? Well, I think he understood things very well. Now let's turn to online questions. Do you have a question for Mr. Hera? Yes. A question about Mandelbrot's set, which you zoomed in very elegantly. How is it possible that the simple equation can contain so much information? I think it was clearly shown that, well, indeed, the equation is quite simple. I can even write down the equation. What you do with the Mandelbrot set is that you say Zn plus 1 equals Zn to the square plus a constant. Zn is a complex number. So you have a succession of numbers starting with 0, and then you write 0 to the square plus a constant plus c to the square plus the constant, etc., etc. And the question is, does Zn tend to the infinite or not? Oh, I'm sorry, I forgot to show you my screen. I wrote things down without you seeing them. There you are. You have this very easy iteration. The only subtlety is that this number is a complex number, and therefore is represented not by a point on a line, but a point on a plane. The question is, does this succession of numbers tend to the infinite or not? Well, it depends on the value of c. And Mandelbrot's set is the whole set of values of c such as Zn does not tend towards the infinite. The uncolored part of Mandelbrot's set is the succession of all points where this equation tends towards the infinite. Once you are over 10, you know that you're going to tend towards the infinite. So the question is, how many iterations do you need until you reach 10? And then you color the point accordingly. This is the mathematical procedure which generates that Mandelbrot's set. Well, obviously, this set has a very complicated fractal structure, but which remains self-similar. When you zoom in, you see new details appearing, but there is no new information. When you zoom in, you get the feeling that what you're seeing looks like what you've just seen before. There is a very similar structure in Mandelbrot's set at different scales. You'll always see things that look like each other. So there is, in that sense, not an infinity of pieces of information. This, I hope, contributes to answering your question. Yes, indeed. Another question, is there a link between the various theories you've indicated and other types of work in other branches of mathematics, like Ekpz or Alexander Kantonik? Are you working in different areas, or are these theories converging in a way? Are there links between all these theories? Well, yes, indeed. To give you an example, these mathematical objects, these equations with stochastic partial differential equations with Kpz points, the analysis of such equations has a lot of similarity with the analysis of field quantum theory. You could have the feeling that it is a completely different theory, which is used in physics to describe fundamental physics and particle physics. And when you try to describe the theory of quantum fields, you have exactly the same problem. You see infinite appear here and there, and you'd like to change the parameters to be able to create kind of things cancelling out each other. Even though the formulation of all these theories is very different, conceptually, they are very close to each other. The algebraic structures that you find on both areas are very similar. So I think that many things can be taken from one field and applied to the other. And that is a kind of situation that you come across very often in mathematics. When you study a mathematical system, you work in a specific area, but suddenly you come up with a question that is linked to a completely different area and requires you to import math from another area. That happens all the time. Yes, but how does it happen? I imagine that you're sitting at your desk in your office and thinking about something. How do you come to that kind of cross-pollination, if I may say so? Well, suddenly you come across a problem and you notice that, for example, there is an algebraic structure, for example, that comes up naturally when you study the problem you're looking at. And then suddenly you remember a presentation that you've attended 5 years ago where the speaker mentioned something that was quite similar. Maybe I should have a look at it. Maybe it's the same structure, and maybe I can learn something from that structure. And then you go and fetch the paper. That kind of situation happens very often. As a researcher, you need to know and be aware of what's happening in other areas of mathematics. In that way, when you see the problem, you recognize it. Let me go back to the issue of infinite. Oh, you wanted to make a comment? Okay. Well, nevertheless, I'm saying this for the non-initiated audience. I think, nevertheless, that there are forms of mathematics that are very different from what we've been discussing this week. Number theory, for example. I haven't seen any connection. Distribution of prime numbers doesn't seem to be stochastic in any way. This is just what I wanted to add. So I wanted to come back to the notion of infinite. You mentioned your area of strongly nonlinear stochastic partial differential equations. I'm not going to go into the details of all the terms of this notion, but you say that sometimes there is no solution to these equations, and sometimes you can even not really figure out what could be a solution. So isn't that a bit weird in a way? How do you manage that kind of situations? What can be observed here is the equation you want to write is an idealized mathematical object. Let me go back to the Brownian movement. And if you take Lorenz's system at large scale, it behaves like a Brownian movement. But at smaller scales, the curve is much plane. But at larger scales, the movement of the curve is much more erratic. In that kind of stochastic partial differential equations, you start studying flat equations or equations where the solution is flat, where you have no problem finding a solution, and then you try to change the scale. Or you bring the scale at which the solutions are flat close to zero. At the limit, you'll probably get something which is idealized and is not flat any longer. So the equation you started with has lost its meaning, but you may have shown that whatever the procedure you've applied, you reach a certain limit, and then you can interpret that limit as a form of solution to your equation. Do you have any other questions? A last question here online, linking the beginning of your presentation with the end of your presentation. At the beginning, you showed this zooming out from atoms to the universe. At the beginning, you've got quantum physics, and at the end of the zoom, you were at the scale of the universe and therefore in the physics of relativity. So the question is there any transition phase from quantum physics to relativity? And can this be mathematically explained? This is obviously one of the major questions of modern theoretical physics. Is there a theory of everything containing both general relativity and quantum mechanics? And for the time being, such a theory doesn't exist yet. There is no good theory incorporating both general relativity and quantum mechanics. Indeed, what we would like to have would be one single theory including everything, where you could find both quantum mechanics at smaller scales and general relativity at larger scales. For the time being, nobody knows how you could reach that solution, unfortunately. But in practical terms, it's very rare that you have systems where both scales play a major part. In most systems, in most physical systems that you can study, you apply either quantum mechanics or general relativity, or none of both. In other words, classical mechanics, which is more or less in between. And in that kind of situations, there is no problem. And then in some extreme cases, we would indeed like to be able to combine both theories. It's possible to do that on an ad hoc basis, but for the time being, we don't have any general theory, including everything. I have a more practical question. You've mentioned using computers to verify theories. But the day before yesterday or last week, I read a paper in the MIT review saying that artificial intelligence had been used to solve problems. Maybe that may sound weird to you, but in our 21st century, with the computation performance of computers and artificial intelligence, do you think that it may help you imagine new solutions or new equations or new theories? Well, not really for the time being. For example, the article you mentioned, well, artificial intelligence is a word that you could really question. There is hardly any intelligence behind that. It's just an algorithm. But in this specific case, it's an algorithm to solve equations or stochastic partial differential equations. There are algorithms to solve these equations, but they tend to be very expensive in terms of calculation or computation time. If you want to calculate the solution of differential equations at large scales with meteorological simulations, for example, that would cost you a lot of time, of computer time. So you'd always want to look for ways to improve these algorithms and obtain solutions more rapidly. This is the case of people in Caltech who were inspired by artificial intelligence models, creating algorithms that help solving differential equations without having to understand what the equation actually means. So you give the algorithm many different pieces of information, and then the algorithm is going to learn in a way how to solve the equation. And once the algorithm is sufficiently trained, it can be very fast. But it's rather a question of engineering. The problem of such algorithms is that there is hardly any evidence that these algorithms work the way they are supposed to. There is no mathematical proof saying that under such and such a circumstance you can guarantee that the algorithm has certain precision. This is one of the major problems with artificial intelligence. It's very difficult to analyze what's happening really behind the scenes. It works, but it's very difficult to guarantee that it's going to work next time. And it doesn't really have much to do with a demonstration of a theorem. That kind of, in inverted commas, intelligence that was mentioned in this paper is just unable to demonstrate a theorem or even to conjecture a theorem. It's an engineering tool to solve equations in an approximate way faster. I'd like to ask you a final question about the Fields Medal and the Breakthrough Prize. Does that give you a specific status? Do you find you're a kind of an ambassador for mathematics? Does that give you a kind of feeling of responsibility? Do you think that you're supposed to talk about mathematics or not at all? Yes, obviously, necessarily. Are you asked to do that more often? Well, yes, indeed. Once you have been a laureate of that kind of prestigious prize, the media come to see you and you have to talk to the general public more than to specialists. And I like to do that, so it doesn't bother me at all. I don't mind. I have no problem being an ambassador for mathematics. From that point of view, obviously, you have a certain responsibility. But in the community of mathematicians, you certainly get a special status when you receive the medal, but later on, it doesn't change much. You remain a member of that community just like the other ones, and the relationship with other mathematicians don't change. As far as the newcomers, the new generation of mathematicians are concerned, does that change anything? Well, I hope I'm going to help indeed, yes. There is another problem with mathematics. Certain prizes are endowed with huge sums of money. Is that a kind of motivation for you? Not really. No, I don't think it is a direct motivation. If you were motivated by money, you wouldn't probably study math. There is a saying in mathematics that there are many other ways of earning $1 million than solving equations. Do you have another question online? Yes. By what were you most influenced when you studied mathematics in Geneva? On Monday, Etienne Guis showed us the Lorentz attractor. You did so too. Why didn't you choose really that type of studies? But is it be linked to the studies in Geneva? Is it a kind of inspiration? Who were you inspired by? Obviously, Jean-Pierre was a great source of influence on me when I studied in Geneva. I think I learned a lot from him and from his approach, his way of looking at mathematics, the fact that he considered it as a kind of game and not as a science. We all have different trajectories, of course. Personally, I started reading physics at the university, and then I came back to mathematics, and my PhD, obviously, was officially about physics, but to be quite honest, it was a PhD on math, even though Jean-Pierre considers himself as a physicist. I think he's actually more of a mathematician. What I was most influenced by was the time I spent with Jean-Pierre discussing with him and with his other students. This influenced my point of view and my view on science. Mr. Ekman, what would you like to tell your former student? What is your message to him? Well, for the general public who doesn't know that, I must say that being a student with me meant that you had to come with me and take a coffee every day at 9 and at 3 in the afternoon. Last question on the Fields Medal, or rather Fields Medals. France, the United States, the United Kingdom, and Russia have the greatest number of Fields Medal laureates. How come? How do we know where the next laureate is going to come from? How can you explain that? Yes, indeed, there are kind of schools, and that certainly plays a part. But the countries you named are also, if you take the number of mathematicians, the countries where you find a great many mathematicians and the great portion of the mathematicians community. Universities in these countries have a very good reputation indeed, and very often go there to study. So that is the explanation. I think we're coming close to the end of this evening. I suppose that you've watched the first two speakers. I have a question about the origin of mathematics. Is it a creation of the spirit or a description of mathematics? Do you invent mathematics or do you construct them? Well, for me, the answer is a little bit of both. I'm not sure that a distinction should be made between the two. It's just like a composer. When he writes a piece of music, that music, once it has been written, it exists and could be interpreted differently and played differently, could be studied. But on the other hand, it comes from the mind of that creator. Mathematical objects are being created indeed, but once they're created, they exist. And other people can study them, can play with them, can look at them from all angles. So for me, there is no contradiction between the two. Mr. Ekman, what do you think about that? No. No. So that would be the last word for this evening. Thank you very much. Thank you for the discussion. And this is the end of the meeting. Tomorrow, Alain Cohn and Sarah Sermandada from ID News will replace me. To conclude this evening, as usual, I want to thank you all for attending this evening. Thanks to the Wright Foundation, to Mr. Courvoisier for having organized this colloquium. Thanks to the University of Geneva for welcoming us here. Thanks to the interpreters who worked into English. And thanks to everybody who helped preparing this evening. Tomorrow, Anacon, and on Friday, the last conference should be online or on the screen with Stanislav Smirnov from the Geneva University. Last thing, there should be a sound and light show at the Parc des Bastions, but it has been postponed to 2021, and the dates will be communicated later on. An exhibition, Belle Mat, was supposed to take place and here in the university, but it's been transposed online. You can watch it and see it on the website of the colloquium. I'm looking forward to find you all back for the next conferences, and take care and have a nice evening.